take a problem on flitched beam. Here we have a question. I am marking this question. Let us read first what is given here. A timber beam 100 mm wide by 150 mm deep is to be strengthened by two plates 100 mm into 12 mm and 100 mm into 6 mm full stop. The thicker plate is secured to the top surface and thinner plate to the lower surface as shown in figure. Here they have provided us with a diagram in which they are showing that the overall width of this flitched beam is 100 mm. The overall depth is given for wooden section, it is 150 mm, and they are telling us that we have two steel plates, one is thick, other is thin. Thicker steel plate is at the top, thinner steel plate is at the bottom. Next, the maximum permissible stress in steel is 120 megapascal and the value of modular ratio is 20 full stop. Calculate moment of resistance of strengthened section. Also calculate maximum stress in timber. Now, this is the problem of flitched beam which we have in front of us. For solving this problem, we need to write the data first. So let us start with writing the data for this problem. First of all, whatever diagram they have given, that diagram we have to draw it again in the data. So I am drawing the diagram of a flitched beam. This is the flitched beam which is given in the question, where the middle section is made up of wood and at top and bottom we have two steel plates. Now I would be writing the dimensions what is given here. This flitched beam is 100 mm wide. The wooden part of the flitched beam made up of, you can say, wood, that is 150 mm deep. Then at top and bottom we have two steel plates. The top steel plate is having its height as 12 mm. Bottom steel plate has 6 mm. Now this is the flitched beam which we have. Apart from this, we would write the next part in the data, that the maximum permissible stress in steel is 120 megapascal. So it is the maximum stress in steel. I will write it as sigma S. Since it is maximum, so sigma S max, it means maximum stress in steel, that is 120 megapascal. And value of modular ratio is 20. So small m is equal to 20. Calculate moment of resistance of strengthened section. That is the first part. We have to find out what is the value of m suffix r, moment of resistance. And the second question is also calculate maximum stress in timber. That is, I have to find out how much is the maximum stress in timber. So here we have these questions and now we would be starting to solve this problem. Now, whenever they give you the problem of flitched beam, first of all try to get the location of neutral axis. Neutral axis is that axis over which the bending stress would be 0. So now here I have a diagram which is given to me. What I would be doing is that replacing this wood section by steel section so that I have throughout steel. You can even solve this problem by converting the steel section into wooden section. Both the ways it is possible to get the solution. So what I would be doing here is that converting the wooden section into the steel section. So in my solution part, first of all, I would be saying that since modular ratio small m is equal to, it is given as 20, and that modular ratio can also be written as width of wood upon width of steel. So therefore if I want to calculate how much should be the width of steel to replace this wooden section, that would be B suffix S is equal to the width of wood divided by 20. Here we have width of wood as 100 mm divided by 20. So therefore the width of steel section which would be replacing the wooden section, that is 5 mm. So in the problem, the first step was to convert the given section into steel throughout. Like I have converted wood into steel, you can even solve this problem by converting steel into wood. In that case, you have to find out how much should be the width of steel, or you can say the steel which is replaced with the wood, that width you should know. Next, so this diagram would be converted. Now, I have converted this wooden section into a steel section. So throughout I have only steel here. I would be marking the dimensions here. 100 mm is the width at bottom. Similarly, 100 mm is the width at top level. Next, the thickness of the top layer is 12, which we already have, and the thickness of the bottom layer is 6. The width of this section, which I have converted from wood to steel, is 5 mm, and its height is 150 mm. So this is the diagram which I have in front of me. I would be solving whatever is asked based on this diagram, because I have converted wood into steel and this is the equivalent diagram which we have. So I can write here that this is the equivalent diagram in steel. Next, here I can see that it is an I section. So I need to get the location of neutral axis here. Neutral axis, as we know, it is that axis at which the bending stress is 0. So I need to know where this axis is there in the section. So for that purpose, what I would be doing, I would be dividing this entire figure, this I section, into 3 different sections. That would give me, this would be, I will be calling it as my first section, and here I have my second section, and at the top I had my third section. Now based on these 3 sections, I would be calculating the value of y bar, because the distance y would give me the location of horizontal axis. After this, I will be saying that since location of neutral axis is given by y bar is equal to a1 y1 plus a2 y2 plus a3 y3 upon area 1 plus area 2 plus area 3. Therefore, y bar is equal to area 1 is this bottom rectangle having width 100 and depth 6, so it is 100 into 6 multiplied by y1. y1 will be the location of x-axis for first rectangle, so it would be at half of 6, that is 6 by 2, plus area 2 will be given by this middle portion, or you can say web, having width 5 mm and depth 150, so it is 5 into 150 area multiplied by the location of x-axis for the second rectangle is, second rectangle as we see it is starting after 6 mm, So it is 6 plus 150 by 2 plus area 3, that is having value 100 into 12 multiplied by y3. This third rectangle is starting after 6 plus 50, 156 mm. So it is 156 plus x-axis for the third rectangle would be at half of 12. So 6 by 2. So 156 plus 6 by 2 divided by area 1, which is 100 into 6, plus area 2, which is 5 into 150, plus area 3, which is 100 into 12. From this, I would be getting the value of y bar, which I have already calculated, and that answer comes out to be 100.76 mm. Now this location of y bar is from bottom. Therefore, y bar will be equal to, from the total depth, if I see the total depth, it is 6 plus 150. 156 plus 12, that gives me 168. So 168 minus 100.76, that comes out to be 67.24 mm from top. So now I have the location of neutral axis, which I can show it on the diagram. 100.76 mm from bottom. This is my neutral axis. The distance is 100.76 mm from bottom. From the top, it is 67.24 mm. So I have the location of neutral axis from bottom and top. Now after this, I would be see the first question as we see. Here we have moment of resistance. So I would be writing how to get moment of resistance. After getting y bar, we can write moment of resistance from using the flexural formula. I can say that since by the flexural formula, from this formula we have m upon I is equal to sigma b upon y. Since I want to calculate moment of resistance, so for m I have to add suffix r. Therefore, m suffix r will be equal to, I would be shifted onto the other side, I divided by y into sigma b. I will keep this moment of resistance as my first equation. If I get the value of I, if I know the value of y and sigma b, my problem gets solved. So here I would be going first for the calculation of I, which is the moment of inertia of the section. So let us start calculating it. Now, since moment of inertia of the section is given by, I will write down I is equal to, since here I have three different sections, that is rectangle 1, 2 and 3. I want to calculate moment of inertia for first, second and third rectangle about the horizontal axis, which is parallel to neutral axis. So here this would be Ix1 plus Ix2 plus Ix3. keeping this as my second equation. Now individually I would be calculating Ixx1, Ixx2, Ixx3, putting the value in equation number 2 to get the value of I. So first, starting with Ixx1. Now Ixx1 will be equal to I1 plus area 1 into h1 square, that is by using parallel axis theorem. Therefore Ixx1 is equal to I1 is the moment of inertia for rectangle number 1 about its own horizontal axis. So about this horizontal axis, the moment of inertia is rectangle 1 is having width b and depth 6. Okay, so width is 100, depth is 6. So it is BD cube by 12, that is 100 into 6 cube divided by 12. Plus area 1 is 100 into 6. H1 is the distance between the neutral axis and the horizontal axis of rectangle 1. So the distance would be 100.76 minus 3 mm. We have to calculate this distance. This is H1 for us. Okay. So H1 is 100.76 minus 3 mm. So 100.76 minus 3 whole square. So from this, if I calculate, I would be getting Ixx1 value as 5.78 into 10 raised to 6 mm raised to 4. Similarly, I would be calculating Ixx2 and Ixx3. So Ixx2 will be equal to I2 plus area 2 into h2 square. This is again by parallel axis theorem. So therefore Ixx2 will be equal to I2, that is for the second rectangle. Second rectangle is having width 5 mm. Its height is 150. So BD cube by 12, that is 5 into 150 cube divided by 12. Plus area 2 is 5 into 150. H2, that is the distance between the neutral axis and the horizontal axis of rectangle 2. Horizontal axis of rectangle 2 would be passing through half of 150, that is 75 mm from bottom. It would be from here, it is 75 mm. I want to calculate the distance between neutral axis and the horizontal axis of rectangle 2. So that would be 100.76 minus 75 plus 6. I hope you all are getting this. That is 100.76 minus 81. That will give me the answer of H2, distance between neutral axis and the axis of second rectangle. So it is 100.76 minus 81 whole square. Therefore, if I calculate all the values here, I would be getting my answer of Ixx2 as 1.70 into 10 raised to 6 mm raised to 4. Similarly, at last we would be calculating Ixx3. So Ixx3 would again be I3 plus area 3 into h3 whole square. And this is again by parallel axis theorem. Therefore, Ixx3 will be equal to I3 for the third rectangle. Width is 100 and depth is 12 mm. So BD cube by 12 means 100 into 12 cube by 12 plus 100 into 12. H3 is the distance between the horizontal line, or you can say horizontal x-axis of third rectangle, and the neutral axis. Now this distance is my H3. In other words, H3 is 67.24 minus half of 12, that is 6. So 67.24 minus 6 whole square. From this, I would be getting Ix63 is equal to 4.51 into 10 raised to 6 mm raised to 4. So here I have all three values, Ix61, Ix62, Ix63. I will be saying that put Ix61, Ix62 and Ix63 in equation number 2. So therefore, if I look into equation number 2, here I have capital I is equal to Ix61, whose value is 5.78 10 raised to 6, plus Ix62, value is 1.70 10 raised to 6, plus Ix63, the value is 4.51 10 raised to 6. If I add up all these values, my answer of I will be 11.95 into 10 raised to 6 mm raised to 4. So now I have the value of moment of inertia. Next thing is that in equation number 1, because we need to calculate moment of resistance, I value we have calculated, we need to know what is Y. Now this Y would be the maximum value of Y, because at Y is equal to maximum value, bending stress is also maximum and moment of resistance is also maximum. So whenever we are calculating moment of resistance, we need to calculate the maximum moment of resistance. So we would be going on to this Y. If I show you the diagram, out of the two values, that is 100.76 and 67.24, we have to select the maximum value of Y. So my maximum value of Y is 100.76 mm. I will say that therefore Y is equal to Y max, and that Y max is 100.76 mm. And in the problem, they have given us the maximum stress in steel. So the maximum stress in steel would be at a distance of 100.76 mm from the bottom. So at this layer, we are having maximum stress, and that was given in the problem as sigma is max, maximum stress in steel, 120 megapascal. Now I can easily put all values in equation number 1 to get my answer of moment of resistance. I'll say that put all values in equation number 1. Therefore, my moment of resistance will be equal to, if we look into equation 1, here I was having I upon Y into sigma B. I value is 11.95 10 raised to 6. Divided by Y is Y max 100.76. Multiplied by sigma B, that is 120 megapascal for steel, 120. Therefore, my moment of resistance answer will be 14.23 into 10 raised to 6 Newton millimeter, which I can even convert into 14.23 kilonewton meter. This is my first answer. The second part is moment of resistance we have already calculated. The second part in this question is maximum stress in timber that we have to calculate. So for that, what I would be doing, I would be drawing a stress diagram to explain it to you all how to get maximum stress in timber. This is the stress diagram which we have, in which the maximum stress in steel at the bottom layer that we have calculated sigma S. This is 120 Newton per mm square. Now they are telling us to calculate the maximum stress in timber. Maximum stress in timber will be at the location where timber meets steel at the bottom. Why we are not calculating at top? Because we can understand from the values of Y that maximum stress would be there in the bottom section because it is far away from the neutral axis. So now I need to calculate the stress in steel. First I have the value of stress in steel at the extrememost layer, which is 100.76 mm distance. Now I would be calculating the stress in steel at the location where it is meeting timber, and that I will call it as sigma S dash. This sigma S dash value will be less than 120 because it is closer to neutral axis. So the more the value is away from neutral axis, that layer would be having maximum stress. So I need to calculate sigma S dash. The distance of sigma S dash would be from the neutral axis. I want to know this distance, and that distance is 94.76 mm. Why it is 94.76 mm is that from the bottom up to neutral axis it is 100.76. I need to calculate from neutral axis to the intersection of wood and steel. So that is 100.76 minus 6. So it comes out to be 94.76. So I would first be calculating the value of steel, you can say stress in steel at this intersection of timber and steel, and then I would be using modular ratio formula to get the answer of maximum stress in timber. So after this, I will say that from similarity of triangle, from the similarity of triangles, here we can see sigma S, that is for outer triangle, sigma S is at distance of 100.76. So I would be writing this as sigma S upon its distance, sigma S that is maximum upon its distance, which is 100.76, is equal to, for this smaller triangle I have sigma S dash located at a distance of 94.76 mm. Sigma S dash is at 94.76 mm. So from this I can say that therefore sigma S dash is equal to sigma S max, which is 120 upon 100.76. I will send 94.76 onto the other side. So therefore I have sigma S dash value that comes out to be 112.85 Newton per mm square. Now once I know the value at the intersection, or you can say at the junction where wood and steel are meeting, now I can easily calculate the maximum stress in timber. After this, I'll say that since modular ratio M will be equal to the stress in steel at the junction of timber upon, at that junction only we would be getting the maximum stress in timber. So therefore maximum stress in timber will be equal to sigma S dash 112.85 divided by modular ratio, which was given in the problem as 20, So from this I am getting sigma T max, that is the maximum stress in timber. It comes out to be 5.64 Newton per mm square, and that's my second answer. So if I look into this question, they were telling us to calculate two things. First was moment of resistance. We had calculated moment of resistance, value was 14.23 kilonewton meter. The second part was maximum stress in timber, that we have calculated. The answer is 5.64 Newton per mm square. With this we complete the question.